Okay, so we're going to continue applying the equation that we just developed for formal charge to the other atoms in all these other resonance structures. So we'll start with this one. We already calculated this first nitrogen has a formal charge of 0. And the first few times you go through this, it will seem very tedious, but once you get more practice with it, it becomes a much quicker process. So let's look at an example of that. And we'll just use the equation form of this. So our formal charge on this nitrogen, we're still starting with 5 valence electrons in the free nitrogen. That's never going to change. Our bonding, plus 0 non-bonding electrons. All right, so there's no lone pairs on this nitrogen. And then we have 8 electrons here and here in bonds, so we divide by 2. All right, and that's not a, I have a error there. That's not a plus there, it should be a minus there. All right, so what we get is 5 minus 4, which is equal to plus 1. Right, you can represent this by a plus 1 or just a plus on that nitrogen there. Let's go ahead and repeat this for oxygen. Formal charge, okay, we start with 6 valence electrons in oxygen, in the free oxygen, minus we have 6 electrons in lone pairs and non-bonding electrons, so we get 6 there. And then we have 2 electrons in a bond, divide by 2, so we'll end up with 6 minus 7, which is equal to negative 1. Right, so oxygen has a negative 1 formal charge in this particular structure. Okay, so a couple of things to note about formal charges. Number 1, if you add up all the formal charges, it should equal the charge on the species. So in this case, we have a neutral species, so the overall charge is equal to 0. And so our formal charges, if we add them all up, should equal 0 as well. So we have 0 plus 1 minus 1, check. All the formal charges add up to 0. So that's one way you can double check that you've done the formal charges correctly. Okay, other things to know about formal charges. We would like to have formal charges that are, if we have, the best structure for an atom will minimize the formal charges. Right, so that's our first principle related to formal charges. So best structure minimizes formal charges. So there are sort of numbers of electrons that atoms will sort of prefer to have in this formal charge setup, and that matches up with, they want to be sharing sort of the correct number of electrons that gives them the lowest possible formal charge, right? So the fact that this structure has formal charges, has a plus 1 and a minus 1 formal charge, means it may not be the best structure. Now sometimes your best structure does end up still having some formal charges on it, especially if you're looking at ions, because then the overall charge is not equal to 0. So that's our first principle. Best structure minimizes formal charges. Let's look at the other two structures that we came up with for this molecule. All right, so let's give ourselves some more space here and look at the difference and decide which of these structures does actually minimize those formal charges. Okay, so we'll go to the one where we have nitrogen, and a triple bonded oxygen instead of a triple bonded nitrogen on the other side. Okay, so let's go ahead and calculate the formal charge of this nitrogen here. So we have, again, our formal charge is equal to 5. We start with 5 valence electrons in free nitrogen, minus 6 electrons in non-bonding electrons, plus 2 over 2, or 2 electrons in our bond here. So that gives us a formal charge of 5 minus 7, which is equal to negative 2. All right, this is already, we can tell, a worse structure because we have a very large formal charge on this nitrogen. Very large meaning not close to 0, right? So it's a little bit further away. All right, we'll look at our central nitrogen. So we have a formal charge is equal to 5 minus 0 non-bonding electrons. This is going to look the same, sorry, not 4, but 8 over 2. It is 4, but 8 total bonding electrons divided by 2. We're pretending they're equally shared. Gives us 5 minus 4. So it's the same as our previous structure. We get a plus 1 here. All right? And based on the rule that all the formal charges should add up to the overall charge of the species, we can guess that the formal charge on oxygen should be plus 1 as well, or else the formal charges don't work out for this. but we'll also go through the equation just to make sure of that. All right, so for this oxygen, our formal charge, we start with 6 valence electrons in the free oxygen minus 2 electrons that are non-bonding plus 6 electrons in bonds over 2. And that gives us 6 minus 5, which is equal to plus 1. Okay, so our formal charges do add up. And this structure is even worse than the previous one. So we want to minimize formal charges, have them be as small as possible. These formal charges are even bigger than our first example. So this is a less important structure. This is a worse structure for N2O. All right, and now we'll look at our last one where we have double bonds to either side. All right, so nitrogen, double bonded to nitrogen here, oxygen here. All right, let's calculate the formal charges here. So formal charge for nitrogen on the left is equal to 5 minus 4 plus 4 over 2. All right, that gives us 5 minus 6, which is equal to -1. All right, so we have -1 formal charge here. All right, here we have a formal charge of 5 minus 0 plus 8 over 4. So the central nitrogen, we keep getting the same formal charge for it because the number of lone pairs never changes on it. So this gives us +1. And then our oxygen here, formal charge is equal to 6 minus 4, because we have our 4 non-bonding electrons. And then we have 4 bonding electrons. We'll divide those by 2, which gives us 6 minus 6, which is equal to 0. All right, so we have -1, +1, and 0. Okay, so one thing we can notice immediately is that none of these structures gives us a structure where all the formal charges are equal to 0. That would be the ideal best structure that we could get. So that is not what we observe in any of these. So then we want the ones that minimize the formal charges. So we have 2 that sort of tie. We have this structure here where we have a +1. Now all these have a +1 on the central nitrogen, but there's a -1 on the nitrogen over here, and then this structure has the -1 on the oxygen instead. So now we come to the other differentiator between formal charges. So we want to minimize formal charges ideally. If we minimize them as best we could, how do we then decide between other ones? And we want the structure with negative formal charges on the most electronegative atom. Okay, so that means of these 3 structures, the best or the most important resonance structure is going to be our first one. So if we come back up over here, oxygen is further to the right on the periodic table than nitrogen, so it's more electronegative. It's the second most electronegative element. It generally likes to have negative charges on it. So this structure here is our best structure, or sometimes it's also phrased as the most important structure. So it's not to say that these other structures are not valid resonance structures, just that they contribute less to the overall electron configuration of the molecule. So our molecule is most going to look like a triple bonded nitrogen and a single bonded oxygen, but because of the resonance, we still will have some character of some of those electrons being shared. So our oxygen will not be strictly a single bond. It'll still have some character of these other resonance structures where we have this triple bond or double bond here. But it's most going to resemble this structure here. Kind of hard to represent that sort of graphically, but this is the most important resonance structure, but these other ones still contribute, just less important. Okay, so that's our introduction to formal charges. We'll do one more video going through another example and coming back to some other structures that we've seen before and why we prefer particular ones versus others.